Hello and welcome. Today we're diving into the hidden physics that literally holds our world together. You know, from the massive bridges we drive across to the very bones inside our bodies, there's this constant, invisible battle of forces going on. It explains why things bend, why they stretch, and maybe most importantly, why they don't break. So let's figure out how it all works.
I mean, you've seen this everywhere, right? At any construction site, on any huge building, it's always that classic I shape. And that's no accident. It's not just for looks. It is a brilliant piece of engineering. So why not a solid square beam or a tube? There's a really good reason, and we are absolutely going to get to the bottom of it.
And then there's the human body itself. Just look at this incredible human pyramid. The person at the very bottom is supporting the weight of several other people. How on earth do their bones handle that incredible crushing force without just snapping? Well, physics has the answer, and it's actually beautiful in its simplicity.
To answer any of these questions, we have to start with the basics, the fundamental properties of materials. So let's jump right into the world of elasticity.
You know, this kind of goes against what we feel every day. We think of a steel bar or a concrete pillar as being perfectly solid, totally rigid. But the truth is, when you apply a force to anything, it deforms. It bends, it stretches, even if it's by a microscopic amount that we could never see. Nothing is truly immovable.
So when things do deform, they basically do it in one of two ways. Think about a rubber band. You stretch it, you let go, and boom, it snaps right back. That's elasticity. Now think of a lump of modeling clay. You squish it, and, well, it just stays squished. That's plasticity. And believe me, that difference is absolutely crucial for an engineer. You want a skyscraper to be elastic, but you'd use plasticity to stamp a piece of metal into a car door. Okay, so to really talk about this like physicists, we need to learn the language. And that language comes down to two key ideas: stress and strain. This is how we describe exactly what's happening inside a material when forces get involved.
So stress is the material's internal reaction. When you pull on that rubber band, the material itself is pulling back, trying with all its might to get back to its original shape. Stress is just a measure of how much of that internal fight-back force is packed into a certain area. It's the material basically screaming, "Hey, leave me alone. I like the way I was."
And if stress is the cause, then strain is the effect. It's that simple. Strain is just the measure of how much the material actually changes shape. It's not a fixed number. It's a fraction, like what's the change in length compared to the original length. So if something has a strain of 0.01, it just means it's stretched by 1% of its original size.
So what happens when we just keep adding more and more force? Well, the relationship between stress and strain tells a whole story. You could even call it the life story of a material under pressure. And we can actually graph that story on something called a stress-strain curve.
Now, early on in this story, things are nice and predictable. A brilliant scientist named Robert Hooke figured out that for most materials, if you double the stress, you get double the strain. They're directly proportional. This super simple straight-line relationship is called Hooke's law, and it's the foundation for everything elastic. But as we're about to see, every material has a breaking point.
And this curve shows that story perfectly. First, you're in the elastic region. The material stretches, but it'll always spring back. Everything is fine. Hooke's law is in charge. But if you pull too hard, you hit the yield point. That is the point of no return. Go past that, and you're in the zone of plastic deformation. The material is now permanently damaged. It will never go back to its original shape. Pull even harder, and eventually you hit the fracture point. And snap. Game over.
This story also helps us put materials into two big categories. A ductile material, like a steel wire or a paperclip, has a long, drawn-out plastic deformation phase. It stretches and stretches and stretches, giving you plenty of warning before it finally fails. But a brittle material, like glass or a ceramic plate, has almost no plastic deformation at all. It just follows Hooke's law for a bit and then suddenly shatters into a million pieces.
Okay, so how do we actually compare the stiffness of different things? How do we know for a fact that steel is so much tougher than, say, wood? Well, we can actually give each material a score.
And that score is called Young's modulus. It's really just the stress divided by the strain, but only in that initial, well-behaved elastic region of the curve. You can just think of it as a number that tells you how much a material resists being stretched. A material with a super high Young's modulus, like steel, needs a massive amount of stress to create just a tiny, tiny bit of strain.
And just look at the differences here. Steel clocks in at a Young's modulus of 200 gigapascals.
Wood is way down at 13, and our bones are around 9.4. That number tells you, point blank, that steel is more than 20 times stiffer than bone. That's how much more force it takes to stretch steel by the same amount.
To really put that into perspective, let's look at this number, 2,000 newtons. Now, what does that mean? Well, that's roughly the force it would take to lift over 200 kilograms, or about 450 pounds.
And that massive force is what it takes to stretch just a thin steel wire by a measly 0.1%. That's the power of a high Young's modulus in action. The material is fighting back with an incredible amount of internal stress, basically refusing to deform.
So this leads to a really cool point that kind of flips our everyday language on its head. We tend to think a rubber band is more elastic than a steel wire, right? Because it stretches more easily. But in physics, it's actually the opposite. Steel is considered more elastic because it resists changing its shape so strongly and snaps back with so much more force.
Okay, we've covered the core ideas of stress, strain, and elasticity. Now for the payoff. Let's use everything we've just learned to go back and answer our opening questions and see how these principles literally shape the world around us.
And here it is, the answer to the I-beam mystery. When a beam bends, think about it. The top surface gets squeezed together, that's compression, and the bottom surface gets pulled apart, that's tension. The part right in the middle, it actually experiences very little stress at all. So the I-beam is pure genius because it gets rid of that useless material in the middle and puts all the strength at the top and bottom, exactly where it's needed most.
What this all means is you get the maximum possible strength against bending, but you're using way less material and weight than a solid block of steel. That makes the entire construction project lighter, stronger, and a whole lot cheaper. It's a perfect example of engineering with stress and strain in mind.
All right, for our final big payoff, here's one last number for you. About 10 kilometers. Now, what on earth could that be?
That, believe it or not, is the theoretical maximum height for a mountain here on Earth. That's even taller than Mount Everest. So why is there a limit? Because after a certain point, the incredible weight of the mountain itself creates so much stress at its own base that it actually overcomes the elastic limit of the rock. The rock at the bottom would literally start to flow like a very, very slow-motion plastic, and the mountain would collapse under its own weight. The physics of rock itself defines the very landscape of our planet. So, from the I-beams holding up our cities to the very height of our mountains, these principles of stress and strain are in charge. It's the hidden science that allows us to build things that last. So my final question to you is, now that you know the absolute limits of your materials, what would you design to last forever? Thanks for joining me.